right. So let me begin this lecture. Like I indicated, I'm going to treat this lecture as done. This is a simple regression that we want to do today. A simple regression is just establishing causality. But before we look at a simple regression, we want to look at what covariance and correlation are. Because a simple regression starts with those things. Okay. Covariance and correlation, they all start with the word co. And the word co carries the idea of happening at the same time. Co carries the idea of happening at the same time. So both of them will look at the nexus or the link or the linkage or the association between two variables. Variable X, variable Y. Variable X, variable Y. Now, covariance is actually between negative infinity all the way to positive infinity. That's covariance. It tells you that, the relationship is positive or it is negative, but it doesn't tell you the strength of the relationship. It doesn't tell you how deep the relationship is. It's very difficult to tell you the magnitude of the relationship. So you may have a situation where one is 24, the other is 29. That larger one doesn't mean that it's stronger because it depends on the unit of measurement. So covariance is powerful. You will calculate it, but because it depends on the unit of measurement, we don't normally use it, except when you are doing structural equations modeling, factor analysis, principal component analysis, KNN, and those things. That brings us to the correlation coefficient. It is sometimes called the Pearson's product moment correlation coefficient. Pearson product moment correlation coefficient. As you can see, that is represented by rho with the letter R with a subscript XY, where X is one of the variables, Y is one of the variables. It toggles between -1 and +1. When it is negative, it means the relationship is negative. When it's positive, it means the relationship is positive. Okay. For example, price and quantity demanded have a negative relationship generally for normal good, except for gifting good or luxurious good, where the price and quantity have a positive relationship. So the correlation coefficient, why that one is more important than the covariance is that you can easily interpret it. You see, that one tells you about the magnitude and the direction at the same time. So that one, you will know that higher is actually stronger. And that is the magnitude. The direction is either negative or positive, which covariance does it. But when it comes to the magnitude, it tells you the extent, the strength and the extent of the relationship. Okay. Now, let's try to look at them in detail. Let's look at some relationships that indicate a correlation, okay, or association. Okay, let's take, for example, age and power of vision. What do you think is a relationship? Is it positive or negative? Age and power of vision. That is your eyesight. Is it positive or negative? Now, we have not indicated whether it's strongly positive or strongly negative for now. We just want to know whether it's positive or it's negative. Rita?
It's negative, please.
It's negative. Explain.
So usually we see older people having more problems with their eyesight, having to wear glasses and whatnot, than younger people, which is why I'm saying negative. So
Good.
the older you, thanks.
You didn't complete. The older you get,
the worse your eyesight, or the weaker.
Why don't you connect it with the power of vision? The older you get,
the weaker the power of your vision.
Exactly. All right. So that's it. It's negative. Let's look at the next one. Okay. Running time and calories burning. What is the relationship here? Running time and calories burning. You see, the reason why anybody can say negative, anybody can say positive. So normally when I get someone explaining, then I know that the thing is proper. So running time and calories you're burning, is it negative or positive. And guys, be used to raising your hands, honestly, because this kind of typing one sentence, you see, typing is a lazy work. When you are typing, you write negative. You know, some of the typing are very lazy work. And when you are lazy in talking, you are losing. Because when you talk, you bring out your inside, your body itself, your brain, there's a lot of mechanisms going on in your body as you talk. So don't try to be soppy. So sometimes some of you just type because you don't want to talk. But that negative, a class 1 student can also write negative. A class 2 student can also write positive. So you saying negative doesn't mean you are right, but you explaining like my dear lady just did. That for me shows that you know what you're saying. You're not guessing. If you are,
yeah, that would be positive. As you run, you tend to burn lots of calories.
excellent. And you see, the one who typed negative was wrong. The one who typed negative in the chat was wrong. But you see, that same person could have typed positive, and the person would have thought that, oh yeah, I was correct, like you were correct. But the person is wrong. So normally, if the person had raised their hand, I would have asked him, okay, why are you saying negative? And sometimes the person might not even know why he's saying negative. So it's always important that you get used to raising your hands and then communicating. What I know is that sometimes when you're not paying attention, when you are doing something things, that is when you are not willing to raise your hand. But it does affect you if you do that, because it means that your knowledge is not expanded. And it doesn't make me give you more, because it's based on you talking that I ask you more, then you get more. All right, Afia, that's good. Let's go to the next one. Temperature and ice cream or bottled water sales. Temperature or ice cream or bottled water sales. Dela.
That's a positive correlation.
Why?
And because the warmer the temperature, the more bottles of water that are sold.
Perfect. Excellent. I like the way you use the word the warmer the temperature. Let's go to study time and grade. Study time and grade. What is the relationship? Afia?
Yeah, that would be positive. If you study well, you're likely to have better grades. On the other hand, it can be negative too, because if you don't study, you get poor grades.
That's still positive.
Okay, all right.
Yeah, if you don't study, that is, if you reduce study time, your grade will reduce. That is still positive. If you increase study time, your grade will increase. It's still positive. Okay. Always remember, and that is because you communicated. That's why you can see that on the screen. The arrows going downward together are positive. The arrows going upward together are also positive. But when one is going down and the other is going up, that is when we say that they are negative. If you do get it. Let's go to the next one.
I'm okay.
Price and quantity demanded of normal goods. What is the relationship there? I think this one is negative. I just said it from the onset, so we know that. Blood pressure and age. What is the relationship? What is the association between blood pressure and your age? Yes, Frederick.
It's also positive. The older you get, the more likely you are to have high blood pressure.
Excellent. Very good. Wage and experience. What is the relationship? Wage and experience. Your salary and your experience. Yeah, Dela.
That's a positive correlation because the more experience you have, the likely the increase in your wage.
Good.
Or the higher the wage here.
Excellent. Finally, consumption and savings. Consumption and savings. Frederick.
I think it's negative. The more you spend, the less likely you are to save, or the
Perfect.
less.
Very good. So you got to have these things at the back. This, what you guys said, is called a priori. It's called a priori. Okay, prior knowledge that we know about this. They are all fine. The only thing is that when you have a data and you test this data, it might not be correct. Now you can show us, you can have a scatter plot for correlation. So look at the scatter plot. This is a scatter plot showing a relationship between an X variable, say age, and a Y variable, say blood pressure. Now the first one, what is the correlation there for the first one? What is the correlation? Is it positive or negative? Or none of them? Dela?
It's a positive correlation.
Good. Now, Dela, compare that with the second one. What would you say?
I'd say the second one is also positive, but the first one is quote unquote more positive than the second one.
Good. What about the third one?
Doesn't look like there's a correlation there.
Okay, let's go to the next one. Who can tell me about this next one? This next one. What is the relationship among the three of you?
And that's also negative.
Okay.
All of them, okay, the first and second are negative. But the third one, there's a part, some are negative, some are also a bit positive. We have more positive on the third one. There's
Okay.
a few of them being negative.
What about the first and second?
The first and second are negative.
Equally.
The second one looks, it's not really equally. They're a bit of some are a bit scattered.
So explain. Second one what? First one what?
The first one, it looks a bit scattered.
Mm-hmm.
And when you compare with the second one, that one's still there. It's quite okay, but there are a few ones scattered, but it's more negative as compared to the first one.
It's more negative. So the second one is more negative. Very good. All right. So that's what I wanted to indicate. Okay. So if you look at the first situation, it's strongly positive, but the second one is moderately positive. And Frederick was right. The last one was no correlation. When you look at this second scenario, the first is rather moderately negative. The second is rather strongly negative. And the last one is parabolic or curvilinear. Sometimes it's known as polynomial or quadratic. So this will get deeper as we get to further levels. So it's good to know. See, the reason why this is what it is because correlation can tell you the degree, not just the kind, but the degree. The kind is that is negative or positive, is negative or positive. But the degree is the more negative, more positive, more negative, less negative, no, moderately negative, and all of that. So it tells you the degree, which is really, really good. Now, what is the formula for covariance? This is the formula for covariance. So if you take one of the variables, say the X variable, and then you take the mean from it, and then you take that of the Y variable, each one, and you take the mean from it. You sum these two and divide by the sample size minus 1. That will give you the covariance. That is not the same as a correlation, because the correlation formula is rather this. Now, if you check the formula very carefully, you will know that everything you have on the covariance, the numerator, is the same numerator you have for the correlation. Just that the denominator is different. So if you look at the denominator, it's the same thing you have for the numerator, but this time you are squaring them and then taking the square root. You are squaring the x minus the x bar, and then you take the square root. Then you multiply that by the y minus the y bar. You square that one too, and then take the square root after summing. Now there's another formula you can use to find the correlation coefficient. So you look at it here, you can pick the covariance here, which is a SXY, and then divide that by SX and SY. SX and then SY. Now, when you look at it very carefully, the SX has been given here. So the SY will be the same thing as the SX, but everything you see, every time you see X, you replace it with Y. And this is another way of finding the correlation coefficient. But then the first one in red, that one seems cool. Okay. Now you can calculate that, but note the strength of the association carefully. It can be perfectly negative, strongly negative, moderately negative, weakly negative, or no correlation. And then you can move upward as well. Note that the correlation is said to be weak when it is between 0 and 0.4, and then the other ranges are shown here. All right, so this is how you normally talk about correlation. Okay, whether it's positive or negative, perfect is 1. Perfect is 1. So normally, perfect, we don't even look at it. For example, the relationship between you and yourself is perfect. The relationship between your nose and your nose is perfect. So perfect correlation is not something we discuss, but we tend to discuss very high degree of correlation, fairly high degree, moderately high degree, low degree, and no correlation at all. So note this relationship. Even when you're writing your thesis, dissertation, or long essay, this is important. You will generate a correlation matrix. All right. There are some misuses of correlation. Some people use it wrongly. For example, some people say that if the correlation is strong, then it means that there's a causality. It doesn't mean that. I'll give you an example. For example, suppose that there's a higher increase in buying food. Okay, so there's a very high correlation between expenses or revenues people are getting at Makola, and then higher revenues that people in the hotels are also getting. So Makola people are getting a lot of revenues, okay, or what we call the car boot sales people or shops or kiosk people are getting a lot of revenues at the market. And then the restaurants are also getting a lot of revenues. You check the correlation, it was 0.95. And then you want to establish a causality, but there's no causality. When I say you want to establish causality, you think, I mean, you can even see that there's no causality, okay? Because causality is when you say that the reason why the restaurants are making a lot of revenue is because the Makola people are making a lot of revenue. And that because the Makola people are making a lot of revenue, that is driving. Now, that doesn't make sense. Because normally you would expect, and this is what, normally you will expect that when so many people are going to Makola to go and buy food and then revenues are going up, then it means that they wouldn't normally want to go to the restaurant. So they will keep their money and not want to go and buy food at the supermarkets because they don't want to cook the food, and so they want cheaper food to cook, and so that's why they go and buy. But then at the same time, the restaurant food, people are still buying it, and the restaurants are always making money, equal money. So even though both of them are highly correlated, there is no causal correlation. There's no causal relationship, and it can happen. So when two things are highly correlated, it doesn't mean that the one is causing the other. In fact, it could be that they are all being caused by something separately. Something separately is causing that. So keep this in mind because you will commit that mistake without even realizing you're committing. I have a project for you guys. You see, the reason why I haven't given you the assignment yet is because it's all loaded, packed into one. So by the time you see that assignment, you are going to do everything we've done with one data set. And that is why, I've just held on. Also, some people make the mistake that weak correlation means that there's no relationship. See, the fact that the correlation is weak doesn't mean that there's no relationship at all. There is some relationship, but just that it's weak. Okay. Another mistake people do is that they think that outliers can affect the correlation. Sorry, they don't think that outliers can affect the correlation. Okay. Outliers can affect the correlation coefficient. They can. And they can even affect the regression. We shall look at that deeply, next time. So look at this relationship you see on your screen. My question to you is that, is there an outlier in this graph? Yes, there is an outlier, and you see that outlier on the far top right. Okay. Now, this outlier can affect the correlation coefficient. And we shall see that over time as we look through this. So I'm going to show you a scatter plot of my data, okay, the data sets for you guys. I want to believe I gave you this data set. If I didn't give you, confirm it quickly so that I give it to you. There's this data set. Oops. It's called bottled water. Do you have this data set?
No, please. You go ahead, share with us.
No, please.
Okay. You got a slice, right?
Yes, please.
Okay. I'm trying to. I've sent you the data. I'm not supposed to actually send you all of it because it's got all the solution. Normally, I don't send you all the solution, but you can open that data set and then you can have a look at it. So let me show you the data set now. Okay. So I'm going to show you this data set here. Confirm if you can see the Excel.
Yes, sir, we can.
All right. So when you look at this Excel very well, you will see that we have temperature and then we have bottled water. Okay. I've numbered the individual aspect. There are just 14 observations. So these are like, year 1, year 2, and the bottled water are in sort of thousands. Okay. Let's just focus on just the first 3 columns. That's the data set. So in these first 3 columns of the data set, you can see that when the temperature is 78 degrees Fahrenheit, bottled water was 23. But when the temperature is 92 degrees Fahrenheit, bottled water goes to 31,000. So you can see that there is some sort of relationship. So the first thing you do in Excel is to scatter plot the data. Now, most of you know about scatter plotting in Excel. All you got to do is to just pick on this, the 2 of them like this, Watch what I'm doing carefully. And then you go to insert and select chart and choose scatter. Okay. Once you choose scatter, you get something like this. You can click on the heading and delete the heading. It's always good to delete the heading. Then on the top left, you see quick layout. Quick layout. But you can change the color of the variables. Okay. Then choose quick layout. And then quick layout, you can select layout number. Watch it. Right now, the data has not been labeled. The X and Y axis are not labeled. And for those of you who have gotten the data, you can do it alongside. We'll use this data throughout. So once you choose layout number 9, it will generate a scatter plot plus an entire regression. Now, I don't want to do that yet. All I want to do is to just do the scatter plot. But I just want you to know that you can just do the trend line, create the trend line, and then have that. Okay, have the entire regression line drawn into the scatter plot. But for now, let's just look at the picture of the scatter plot. This is it. You can use several of these to showcase the look of the data set. So these are several ways you can look at the data set. Okay. No fancy thing here. Normally what you do is that you leave it as it is, leave it as it is. Okay. Now, this is original, but I just want the axis, X and Y axis. So watch it. You can just go here and then choose. In fact, you can choose one of the quick layout, okay? That will give you both the X and Y axis, like this one here. Okay. This one here will indicate the X and Y axis. Remove the bottled water, the heading. Never put a heading in the graph. It should always be separate. Remove the legend as well. This is a legend. And then copy the name of the data, which is high temperature. Copy this and then come to the axis title, which is the X, and drop it here at the X axis. Okay. And then you have the full name of the X axis. You can even click on it and bold it, like I've just done. Then go and do the same thing with the bottled water sales. So I copy the bottled water, come to the Y axis. You will do all of this, by the way. Come to the Y axis, and then you also show the axis. Okay. So normally the axis will not show by themselves, but you have to show the axis. So just by looking at this, you create a scatter plot. A scatter plot is a visualization of your data set. And you can clearly see that there appear to be some sort of correlation. It's not perfect. It's not very strong, but there is some correlation between temperature and sales. You can see it is going upward, sort of. Okay. It would have been a perfect correlation if it was something like this, it was going this way, or it would have been high correlation if the data are all lined up like this. But for now, it's not. The scatter plot is the first way you can visualize the relationship. Okay, so now that gives you the scatter plot. What is the next thing to do once you have your scatter plot? You can calculate your correlation. You can calculate the correlation. There are several ways you can calculate the correlation, and I've done it here. So I'm not going to show you the Excel. I'm going to come back here to the slides. Please confirm when you can see the slide.
Yes, please.
Okay, so we can see it now.
All right. Now, this is a data set. As you can see, we want to do covariance first. Remember, we said that covariance. Now, to do the covariance, if you can remember the formula, okay, for the covariance, the formula says that, it says take the X, subtract the mean of X from it. Take the Y, subtract the mean of Y from it. That's what we're going to do here first. So where is the X? The X, we already have them. That is the temperature. Where is the Y? Y is the sales. So you take the X for each and subtract the mean of X. In fact, the mean of X has been calculated. You will see that somewhere like that. think it's at the top here. There's it. It's on the far right here. That's the mean of x, 84 and then 26. So when you take the 76 minus the 84, sorry, 76 minus, the 84, it will give you -6. That's the first one you see here. And when you take the last one, which is 92 minus 84, that will give you positive. That's the last one here, which is 7.36. And so you can do all of these for x and then for y. And then you can find your covariance. Okay. Now, how do you find your covariance? Watch it. Once you've done your x minus x bar, y minus y bar, you multiply each one. So you take this first column, multiply it by the second column. You take the first column, multiply by the second column. Take each first column here, multiply by the second column here, and then you get the values here for each one. When you do that and you finish, you sum all of these values. That will give you 166 here. And according to the formula, you should divide it by n minus 1. What is the n value? Who can tell us? What was the value of n? When you count this, you will know. You will know the value of n.
14.
14. So you do 14 minus 1, that gives you this 13. And then that will give you the final value of 12. So the covariance is 12. Okay. Mind you, you can use Excel to give you the covariance directly instead of calculating it. Now, the next thing you can do after getting the covariance is that you can go ahead and do the correlation. Again, using the formula for the correlation, you can use this SX and SY formula, which I showed you. Okay. And then you can calculate to find this correlation. You can also do your correlation by using this command. So you use this command, correl, equal to correl. And then you select everything from B2 to B16 and everything from B16, C2 to C16. Okay. You just bring a comma between them. And so that would tell the Excel that you want to do the correlation. And when you do that and you click enter, it will give you the correlation of 93%, as you can see here. So this correlation of 93% can be generated immediately on its own. And please remember that the covariance too can be generated immediately without going through the gimmicks. That one is here. So instead of using the word correl, you use covariance.s. The S means sample. And then you use that same range like you did. That will give you the covariance. That will give you the 12.8. So look at the covariance value. It's 12.8. What does it mean? Remember we said that it is positive infinity. So this 12.8, if you want to interpret, is it high or low? You don't even know. That is why we said that it's very difficult to interpret covariance. But it's easy to interpret correlation because the value is 100%. And now we have 0.93 here, which means that it's 93%. It's very, very highly correlated. Temperature and sales here, bottled water sales are highly correlated. So now we are able to establish the correlation between the two of them. You can do this correlation. If the variables are many, you can generate a correlation matrix. I know some of you are aware of this already. Okay. So I've given you a picture of how to do that here. Generate a correlation matrix by clicking Data tab and then going to the far right here, you see Data Analysis. When you click Data Analysis, you see correlation in the list. Once you double click on that, this pop-up will show. In this pop-up, you will enter the input range. You enter the input range, that is select the data. This time you don't select only one. Select everything together with the title, everything in the data together with the title. You select that. After selecting that, you put that in the input range. You will tick columns. You will select labels in the first row. You indicate where you want the results to be, and you click OK. The moment you click OK, you're going to get this correlation matrix right here. And the good thing about this correlation matrix is that it doesn't matter whether the variables are 100. Excel will generate a correlation coefficient for everyone. The one you are looking for is this. And it shows the correlation between temperature and sales. Remember, that was the same value you had when you did it on its own. And that will be the same value you will get when you calculate using the formula. So this last one I did, I've used it a lot on my own publications. It just goes to show that you can easily do some of these things with it. So learn to practice how to do correlation. Remember, correlation is only telling you that there is an association, and the association is strong or weak. It doesn't tell you anything about causality. Now let's go to causality. Causality is regression. Regression is establishing a causal relationship between a dependent variable and an independent variable. You want to pay attention here. Now, a regression starts with a model. By the way, what's a model? A model is a representation of reality. That's a model. If you take a camera and you take a picture and you look at a picture on your phone, that picture is a representation of you, the reality. That picture represents you. You are the reality. The picture is a representation. Therefore, we can say that a picture is a model. There is something about temperature and water bottle sales. And you can represent that as a model. We'll do that pretty soon. But before we do that, I need to tell you some few things. The reason why regression is powerful than correlation is what we're about to show you. You see, the correlation coefficient is this beta 1. So first of all, whenever you are specifying a model, there are two things. This is a simple one. Simple regression means that you have one dependent variable and one independent variable. The dependent variable is the recipient, is the outcome, is a response. The independent variable is a causal factor, is a predictor. So the dependent variable is the one that is responding to the behavior of the independent variable. So if you take, for example, age and blood pressure, which one do you think will be the dependent variable? Age and blood pressure. Which one will be the dependent variable? Which one? Age and blood pressure. Which one will be the dependent variable? Frederick.
Blood pressure.
Very good. So if you are writing this simple regression, you are going to say blood pressure on the right is equal to beta naught plus beta 1 age, and then you do plus the error term. We'll come and talk about the rest. So this is a simple regression of blood pressure and age. Question. Blood pressure is a dependent variable. Age is independent variable. So that leaves us with beta naught. What is beta naught? Beta naught is the intercept. What is the intercept? The beta naught is the intercept. The intercept has no economic meaning. Write it down. Write it down. This one is not in slides. The beta naught has no economic meaning. The intercept has no economic meaning. It is not that, it's for cosmetic purposes. It's for beautification. So even in Excel, when you're doing this thing in Excel, Excel can say that, do you want me to suppress the beta? In other words, do you want a situation where you don't even want to see the beta? Not. It's not too important, but it's highly important when you're doing prediction. Beta naught is important when you're doing prediction. That's one. And two, beta naught is important in a panel regression. That is when you have multiple time periods. That's when beta naught is important. In a simple regression, in a cross-sectional regression, beta naught is not a big deal. Now, what then is beta 1? Now, remember the beta 1 is attached to the independent variables. So it means that if there are other independent variables, there will be beta 2, beta 3, beta 4. Now, let me give you an example. Suppose you have a different model here. Okay, suppose I were to write a different model where you have blood pressure equal to beta naught plus beta 1, the same age, but this time plus beta 2, but the weight of the person, because your weight can affect, plus beta 3. Now we are going into multiple regression here. You can say that, what do you call it? What other things can lead to blood pressure? Let's say other diseases.
Maybe diabetic.
Yeah, other diseases. They all capture into other diseases. I just don't want to bring other diseases. It might confuse the whole thing. Anyway, let's just say stress. And then, of course, your error. So in this case, there are multiple independent variables, and that is called multiple regression. We shall do that next week. Now watch that. The betas, apart from the beta naught, every other beta will have an independent variable. Okay. So what do the betas do? What do the beta that have the independent variable, what are they doing? Well, first of all, remember that each independent variable is trying to influence the dependent variable. So age is influencing blood pressure. Weight is influencing blood pressure. Stress is influencing blood pressure. So the question is that, how much is each one influencing blood pressure? That is what the betas are telling you. So they are telling you by how much. So beta naught measures the marginal effect. The beta 1, beta 2, beta 3, okay, it measures the marginal effect of the independent variable on the dependent variable. Write it down. Write it down. Okay. The beta measures the marginal effect of the independent variable on the dependent variable. It tells you by how much the independent variable affects the dependent variable. That's it. That's what we mean by these betas. Any question on that first? The next thing is, so let me clear these things so we can go back. So each independent variable can say that I am influencing blood pressure. Okay. Each X can say that I'm influencing Y. But the question is that by how much? That's the question. By how much are you influencing Y? That is what the beta will tell you. That leaves us with the last one, which is the error. The error term captures all other factors that can affect the dependent variable, but have not been captured yet. So there are other factors like diabetes, like other diseases, like pulse rate, and several other factors that can affect blood pressure. In fact, poverty level can even probably affect blood pressure. Any other factor that can influence blood pressure, any, is captured in the residual term or the error term. Now, they are sometimes called disturbance term. Write it down. They are sometimes called unsystematic error. They are sometimes called the residuals. They are sometimes known as the unobserved heterogeneity. I ask you these things in the exams. What are the several names for the errors? That's why I'm mentioning them. So this disturbance term, they are disturbance term because they disturb the original relationship variables you have. The other independent variables, the x's, that are affecting the dependent variable, the error is capturing all other factors that can affect the dependent variable. And then you want to capture all of these. You want to capture them, and the error term captures them. You cannot tell. So we call it sometimes disturbance. disturbance term. And why is it disturbance? Because they disturb the relationship between the independent variables and the dependent variables. So guys, that is regression model. Once you estimate the model, please remember every regression model will have an error term. And it will have beta parameters, and then it will have, English parameters. It will have Greek parameters and English parameters. English letter parameters and Greek letter parameters. No numbers, no numbers, no numbers. Write it down. The regression model has no numbers. But then the estimated regression equation, has numbers, and has no error term. So you can see that in the estimated one, the error term is gone. And you'll come to see why. But then they have caps on them, which means that they have been estimated. So once you estimate them, the beta naught is now a number. Once you calculate them, the beta 1 is now a number. And this is a typical example of the estimated equation. It's only the betas that change. The letters don't change. So there's a basic idea of a sample regression. But hey, remember, in our sales example, this is how you would have written the model. I've put it here for you. Because in your exams, I will ask you to do the same thing to formulate the model of certain regression. That one will not even be a simple regression here. It will be multiple regression. So you want to be able to master the basics, the ingredient of how to formulate a regression once you have the data. Yes, Samuel.
Prof, please, why do we have beta naught temperature?
Okay, it's good. That's a typo. It should be 1. You're expecting it to be 1, isn't it? Yeah, it should be 1. The I here indicates that we are dealing with individual variables. In other words, the sales is changing across individuals. If it is also changing across time, you have IT, and that is in the area of panel regression. We will not do that. Okay. So that is how this is supposed to be. So yeah, of course, the beta should be beta 1 and not beta naught for the temperature. And then if there are more, then, for example, sales is not affected by only temperature. Okay. The sales can be affected by other goods. The sales can be affected by time. It can be affected by price. It can be affected by several other. Very good. So that is a model. This is a theory, but there's more. I am now going to put a line into this to create the regression. You see, the essence of regression, and this is with a deep culture you want to appreciate. The essence of a regression is that whilst you have the scatter plot, a regression is trying to put a line here. But why? How? Okay, let me tell you. Before the line can actually be created, a regression makes certain assumptions. So first of all, a regression tries to look at the gap between the predicted and the actual. Now, let me explain. You see the values that are here? This is actual value. It is an actual value where you have X variable here, and then you have Y variable there. Okay, it's an actual value. This one too is an actual value, which has another X variable, okay, and then another Y variable. Now, if I want to find the mean, if I want to find the mean, a dot, that is actually, that is actually in the middle of all of these dots. The only way you can find that is you got to predict what this actual would be if it was to be predicted. And so you have an actual Y, and then you will have a predicted Y. The predicted Y is sometimes called fitted Y, which means there's a gap between the two of them, the gap between the actual and the predicted. And this gap is what is known as the error. The error. Now, if the error is minimized, if you try to, you see, I don't know, okay, I don't know for now, but for now, the dot that was represent all of them, okay, if I'm able to get the dot, the mean dot, the average dot, then I can look at a gap between this actual and then the dot. The dot, of course, becomes a predicted. The gap between the actual and the predicted is the error. And you don't want errors. You don't want errors. What you want is zero errors. So you want to minimize the error as much as possible so that the actual and the predicted will be what? Will be the same. Well, the word expected value of the error is 0 is a reason. You may have heard about that. So we expect the error to be 0. This is one of the major assumptions of regression. It's sometimes called the normality assumption. So we're expecting the error between the actual and the predicted to be 0, so that the actual value will be the same as the predicted value. A regression uses a principle called ordinary least squares, OLS, to minimize the error using the principle of minimization. Minimize the error so much that that minimization process can help us to find the coefficient or the estimate, the beta that we spoke about. Remember, the betas, we don't know them from the beginning. We don't know beta naught, we don't know beta 1, and then if there are more betas. So using that OLS principle, OLS theorem, OLS assumption, sometimes it's known as the Gauss-Markov rule or the classical linear regression assumption. Using that approach, and now we are going to do that in a simple way. Using that approach, you can now find the estimated equation. You can get the numbers, that's what I mean. Now let's try to get a little bit clearer. So what the regression will do is this. All that I said, the regression identifies the actual and then the predicted. The predicted is on the line. For me, I'm more interested in how did you even get a line? But then the line is the average. Anytime you want everything to be compared in life, you normally want to be compared with the average. Well, generally. I don't agree with that, but normally people want to be compared with the average. Oh, I'm even above the average student. I'm even above the average student or a typical student. A typical student, I'm above. But the best is to normally compare yourself with the best, not compare yourself with the average. We don't want to be average. You saw one of my videos, I put there, you don't want to be average. You want to be among the best. But anyway, regression compares you with the average. So if I have this sales, how far is this sales Y1? How far is it from the average sales? Or here, the predicted sales? That is why you see Y1 has been capped here, the predicted sales. How far it is the error. Now, this error is above the line, so it's a positive error. When the error is below the line, it's a negative error. The essence of the OLS regression approach is to minimize this error. Minimize it till the actual comes on top of the line. And that process will help us to get beta parameters. Now, in our own, it's the same thing. You can see that this is the first observation, and the first observation is here. And we created a regression line. You remember when I showed you the scatter plot, I showed you how to create it. So the error here is error 1, because this is observation 1. You can go to this one here, the Excel. Okay. So I've come to the Excel here. And then you can now click on this graph here and go to chart design at the top. And then choose the quick layout on the far left. And then select this one, which is layout number 9. And when you do that layout number 9, which I've done here, these ones are legends, so they don't make the thing look nice. So remove this legend. Also remove the heading. And then this whole graph here, okay, I'm trying to make it clearer. When it is clearer, you can see the line well. Okay, so this line is what I have created here. Okay, so this line that you have created is what is known as the fitted line, the predicted line, the regression line. Anybody that any error that is any observation that is above the line will create a gap, an error between what you are, which is actual, and what you should be, which is a predicted. And then regression will start minimizing the errors in the process. So that's what we are going to do. We are going to understand the principle of this. But there are also some assumptions you want to appreciate when you are doing regression. So how do you find the beta? That's what we are going to do using the OLS. This is how you find the beta. You minimize the errors, also called the residuals, the sum of squares, between the actual value and the predicted value. The actual value of the dependent variable, which is the y, and the predicted value of the dependent variable. So the actual value is the y, the predicted value is the y cap. How do you do that? Well, I want you to remind yourself something small. It's a bit of mathematics, and don't get scared. The regression is actually, the simple regression is y is equal to beta naught plus beta 1 x plus error. This is how it is. Now this error, I can make it the subject and move everything to the right-hand side. So you will now have y minus the beta naught minus the beta 1 x equal to the error. And we have already indicated that this whole thing here is a predicted. Okay, the beta naught plus the beta 1 plus x. Assuming the error is not there, this whole thing is a predicted. Let me use a different color to actually. So this whole thing here is a predicted. So on the basis of that, I can conclude and say that the y minus a predicted is the error. So this is with a premise where you can now start and handle regression and use this principle to find beta 1, beta 2, beta 3. Remember, our goal is to find these parameter estimates, also called coefficient. You see, when you don't understand anything, you have to write it down anytime I speak about it. The coefficients are also called estimates. They are called estimates or parameters. Or actually, not parameters. They are parameters when you have not estimated them. They are parameter estimates or coefficient when you have estimated them, when you have a value for them. So we are going to use that principle to generate the beta parameter. So watch it. I've given you a prelude. So this is a regression model. As you can see, I've gone through this already. Then the error is the y minus the y cap. That is the actual minus the predicted. I've shown you this already. Therefore, the predicted is only given by the beta naught plus the beta 1 x. I've shown you this also already. Okay, now with this, we have to take the square of this error, which means that if we take the square of the error on the right-hand side, we'll take the square of everything. And this is what you get. So watch it. Okay, hold on. Here is my confusion. So what I decided to do first was to take the square of this error. So that means that the whole of this y minus beta naught plus beta 1 x, I also decided to take the square of all of them. Then I take the sum of that square I did. Now, why do we take the sum? Because remember, why do you take the square in the first place? Because the errors can be positive or negative. And because the errors can be positive or negative, if you want to clear positivity, negativity idea, if you want to clear the negatives, you square it. Because when you square it, negatives will vanish. And then you sum the errors. Okay? So that means that now you're going to sum all of these as well. Now that you have the error sum of squares, the goal of the regression is to minimize this error sum of squares. Remember, it's a combined thing. It's a mean of the errors, more or less. So how do you do that? Let's just go back. So this next formula that you see is what I did there. You have the error sum of squares. Now, regression will minimize, and there's a way of minimization. It's called differentiation. Guys, nobody forced you. Now remember that the good old days of integration, differentiation, simultaneous equation, some of these things along the line, you meet them, master's degree. So you would have to differentiate this one first, respect to beta naught, because your goal is to find the beta naught. That's your goal. Your goal is to find the betas. So find the beta naught. That's your goal. And then later you come and find the beta 1. That's your goal. That's your goal. That's your goal of the regression. Now, if you want to find something, you differentiate. And this differentiating comes from the basic differentiation rule. So if you have y is equal to, if you have y equals to, 2x, and you're looking for x, is dy dx. And that will give you what? That will give you 2. It's an old principle. That's what we are going to do here. Okay. Yes, Avia.
I said where we're doing the sum, the b1x, I was expecting it to be a minus sign. Y minus b naught and then minus b1x. I'm seeing a plus there.
Oh, yeah, I know what you mean. I think that I still assume that I had a bracket. Actually, there should have been a bracket here. If there's a bracket, then there's no minus. If there's no bracket, as it is, yes, you're right, there should be a minus. Okay. Yes, Ebenezer.
I wanted to understand instances where we can have negative errors and positive errors. Maybe a real time example. We can see negative or positive errors.
Well, I showed you up there in the graph that if you see, when you are above a mean, the line is like the mean, right? And when you're above the line, it means you are better than the average, isn't it? The line is the average. So let's say that I take the grades of everybody in this class. The average grade is 70. But you, Eben alone, you had 82. Are you above the average or below the average?
I'll be above.
What if you have 42?
That's below.
Okay, so this kind of value of above and value of below, what it means is that some are above, some are below. These are the gaps. We call them the errors. These errors, some are above the mean, some are below the mean. We want to sum them, but you can't sum them because some are below the mean and some are above them. You see, you want to have a bigger picture of the total error. One value for the total error. And that is why. So your understanding of above and below, the minus is simply indicating how far you are from somewhere. Remember, we are also still establishing a relationship. And in fact, if you can remember correlation, we said that correlation can be negative. Do you remember?
Yes, sir.
So how far you are from the mean, which is a line, defines whether you are negative or you are positive in terms of error.
Okay, I do get it now. So, Prof, that when you're measuring the distance, would you just use the how do I call it? Would you use the point or you would use just the gap for maybe using the chart? You just use the line you've written, for instance, the error is you just use the distance between the red point and the line, or you have to use the actual point on the graph to measure the error.
You use the distance between the points, the actual value here, this dot, and the line. Remember, the line is the average of every dot.
I get it.
Wherever whoever is, that line is representing how far he is from the average. Just that, so the line is like many dots. And these many dots is representing each average. But the average is the same for all of them. So you just have to know where you are, and then you compare yourself with that average, because that average is the same for everybody. So look at your actual value, see how far you are from the line, and that becomes your error. I want you to understand that in this context, the error here is positive error doesn't mean that is good, negative error doesn't mean that is bad. Don't attach morality to it. It is how far you are. Whether you are far from it positively or negatively, that is how it is. Let me ask you something. The relationship between price and quantity demanded, is it positive or negative?
But when price is low,
Is it positive or negative? Price and quantity demanded.
to have a negative relation.
So it's negative.
Yes.
Is that good or bad? If somebody increases his price and I decide I won't buy the good because the price is high, is that good or bad for me?
It will depend on who is, if it is on the consumer side, that is.
I say for me, I'm a consumer.
Okay, so it will be good for you.
So you see, negative is good. That's why I'm saying that you cannot attach negativity, morality to this negative and positive. You can't. That's not what we are saying. We are showing simply how far you are from the distance. I know you get a picture.
Yes,
all right.
Yes, I do get it.
So you minimize the error sum of squares, set it to 0, and find the beta naught. That's what I did here. I minimize the error sum of squares, set it to, I'm minimizing with respect to beta naught, set it to 0. So what that means is that you have to take these two, multiply the 2 by the sum in front, and then have everything here. But the 2 will be gone, because when you are minimizing, you subtract 1 from the exponent, set it to 0. Now that you've set it to 0, you expand. So you take minus 2 sigma, multiply it by y, minus 2 sigma, multiply it by beta naught, minus 2 sigma, multiply it by beta 1x. Okay. And then you can manipulate and find the value. That's what you can do it here. Instead of that, you can end it here. Okay. And that is for the beta naught. You can do the same thing for the beta 1. So this one is for the beta 1. I'll conclude on each one of them very soon, don't worry. So you take this one, you also differentiate that whole equation with respect to beta 1. Now remember, when you go to the equation, okay, beta 1 has x attached to it. Of course, you have to take the 2, multiply it by the sigma. Yes, Ebenezer.
So in the differentiation aspect, when we differentiated, we brought -2. I want to understand why it's -2, because I thought we only have...
It's -2 because the beta naught here has a negative in front of it. You normally differentiate and multiply it by the number in front of the letter. Do you see where I'm pointing? There is a negative in front of this beta naught, and we were differentiating with respect to beta naught.
Okay.
And remember that this one is supposed to be negative. Your friend lady mentioned it. So when you expand this, it's supposed to be negative here.
Okay.
You see, this negative will apply to all of them. So each one of them will be negative. And so when you differentiate, you are going to have -2 for each one of them. If your question is answered, you can lower your hand.
Thank you, sir.
So once you do that, now here too, you can expand and then make beta 1 the subject. So first, let's go to beta naught. Let's make beta naught the subject. How do you make beta naught the subject here? Well, if you expand, okay, and you make beta naught the subject, you're going to get something like this. Let's see. Okay. So for the beta 1, remember the beta 1, you will have x, because remember that there will be a square. So you will have x attached to the sum. Remember, this is having to the power 2. So when you bring the power 2 in front, you will have x still left for this one, for the beta 1. Okay. And so let's now go to equation 3 and then make this the subject. So let's go to equation 3 here. This is equation 3. We are looking for beta naught. To get a beta naught, this is it. If you, and again, this one, if you know, you know. If you don't know, you don't know. If you take this summation, you multiply this summation by a constant, you get n. Because remember, the summation is indicating the sample size. So if you multiply it by this, you get n. If you multiply this summation by y, you get like sigma y, okay? But it's also divided by n, so you get a mean. You get a mean for that. Okay? So that is what you see here. So you get sigma y for this, you get n for that. And then for the x, you get sigma beta 1x. Remember, this one had a beta 1 and then plus x as well. You can see that from here. So you are just taking this sigma. Of course, when you have to clear the negative 2 because by dividing both sides by negative 2, okay, so that will clear it to be 0. And then you multiply this sigma by the x, you get sigma x beta 1 or beta 1 sigma x. And then now, once you have this, what you got to do is to just find beta naught. How do you get beta naught from here? Well, what you normally would do is that you divide both sides by the sample size. So you divide both sides by n here, you divide this one by n here, you divide this one by n here. So this sigma y over n becomes like y bar, the mean of y. Okay. This n will cancel, so you now have beta naught. Plus, this one is going to give you x bar, because you're going to get sigma x over n, then beta 1. And sigma x over n is actually s bar. So at the end of the day, you're going to get y bar equals to beta naught plus beta 1 x bar. And now that you want beta naught, you move this one to the side here. And that will give you the rest. In fact, when you do that, of course, that will give you the rest of whatever you are looking for. Let me just show you here. So that will be the final value. So the beta cap I brought on top of this is indicating that I have now gotten the value for the beta naught. Now, how about the beta 1? That one is a little bit tricky because when you go to the equation, watch it here. When you go to this equation here, if you divide both sides by negative 2 and clear the negative 2, then down here, you are left with sigma xy for the first one here. For the second one, you are left with sigma x, sigma x beta naught, or beta naught sigma x. Then the other one, the last one, the x becomes squared. So you now get beta 1 sigma x squared. That's how you get it. So look at it. Now, if you want beta 1, you can now divide both sides by sigma x squared. Each one by sigma x squared. Each one by sigma x squared. Okay. And then the rest will follow. Let me just go back to the next one. Okay. So you just have to take your time and go through this. It's very simple. So that's it here. Okay. Then, now that you want this, you divide both sides by that. And when you divide both sides by that, you will get this value because you will notice that this one here will be gone. Because when you have sigma x, remember this one is just n, beta naught. So beta naught will be gone. So when you divide both sides by sigma x squared, and sigma x squared divided by sigma x squared will be gone. So this one will be gone. Okay. Then the right-hand side, the left-hand side will be the one that is most important. Okay. You're now going to have this. Let me just quickly, because I just realized that. Just a second, let me just, oops. Where is my Zoom? Oh no. Can you guys hear me? Because I can't see my Zoom. I have so many windows open.
Yes, sir, we can hear you.
Okay, just a second. I don't know why. Okay. Oh no. Just a second. Just a second. Let me just. I will not even do this. Change it again. So you will notice that, I'm just going back. You will notice that everything will be off, and now your beta 1 will be sigma yx over that. That is the value you are going to get for this. Of course, this becomes the estimated regression. Once you have these values, once you have this beta naught value and this beta 1 value, you can substitute them into the equation. So your final equation, the estimated regression equation, becomes like this. I wanted you to know mathematically and graphically how to find the beta parameters, because these are the estimates that are used. This is what Excel is doing behind the scenes that you might not know. And that's what Python is also doing behind the scenes. This is your estimated regression equation. Of course, anytime you see y cap is this over that, y bar is this over that. Okay. You have all of this clearly showing in that regard. Did I change something here? I think I changed something here. Toggling between multiple windows. Anyway, so once you got your beta values, you substitute them back into the equation. By the time you finish your estimation, remember that the error would have been 0. And you will see this when we come to the assumptions of regression. So the final values of beta 1 and beta 2 are obtained like this. This is how you get the values. This is another way I can go through how to achieve this one. But note it, this is another way of getting the beta 1. This is another way of getting the beta naught. As for the beta naught here, you already know it. And please remember, you always need to find the beta 1 first, and that will help you to find the beta naught. Okay. So you find the beta 1 first. Now let's take that into, so that is OLS regression. There are other regression approach you can use to also find the betas, because these days there are modern regularization approaches that are used, especially in machine learning, okay, that can be used to get a better sense of the beta 1 and then the beta naught. The whole essence is to ensure that, remember, the beta 1 is an estimator. Okay. Beta 1 cap is an estimate of beta 1. When I say it's an estimate, it is from a sample. So you collect a sample, then you get a value. You collect a sample, then you get a value. And based on the value, you're able to come out with this. Range regression and lasso regression are also able to estimate the coefficients. And the approach one can use to estimate this coefficient is here. I will not go through the nitty-gritties with you. But when you get to your second time, you will learn how we get all of this if you want to. So range regression is a beautiful machine learning approach, apart from the OLS regression, that can be used to estimate this. All of them, we are minimizing the errors, sum of squares, in some unique way. In this case, we add some value to it, to the original OLS approach in the range regression. We add some beta square to it with a lambda. In the lasso regression, you rather take the absolute value of the beta and then work with it. And these two methods are sometimes called the absolute shrinkage and selection operator method. So the software is able to calculate these two easily for you. Another way of finding the betas, of course, I've just shown you the OLS way of finding the betas, but I'm just showing you other way. It's called elastic net. Okay? The elastic net helps to estimate the coefficient again by minimizing. Remember, they are all minimizing the error, which in this case is the OLS1. But they all are adding something. So in this case, the elastic net is adding something else, to the original OLS. Where this second term here, in the second terms, you remember the second terms for the ridge regression was this. The second term, when I say second term, is after the normal OLS. This second term is for the lasso regression, and this second term is for the elastic net. All of this second term are known as the penalty function or the penalty term. Okay, that is it. And you can see that there is a lambda for each one of them. Okay, so if you check the first one, let me just explain this. If you check the flow, if you check the first one here, there's a lambda. Okay, second one, the first one is for the ridge regression. The second one is for the lasso regression. There's also a lambda. The third one is for the elastic net regression. There's a lambda, and 1 minus even the lambda, because that one is splitting. This lambda is called the tuning parameter. Okay? And it tells you the weight of the penalty that one can actually put in the estimation of the beta. In other words, as you estimate the beta, there is a penalty you got to pay for that. So all these three, the ridge, the lasso, and the elastic net, they extend the OLS regression with extra penalty on the importance of the weight. We know the weight is important. We know the beta one is important. We know it tells you how much more the independent variable affects the dependent variable. We know it. Okay, but they indicate more importance to that, by generalizing the equation of the OLS. It's a beautiful new approach. You can use this thing in your thesis. You can just write just in your thesis and compare these three approaches in a thesis. You will have a wonderful result in that regard in your dissertation. Next one is a support vector regression. That is another way you can do. That one is slightly different. It doesn't add up to the OLS at all. If you look at it, that one minimizes the half of the beta square, the half of the sum of the beta square, subject to this equation, less or equal to a certain error parameter. If you compare that to the OLS is this. This is the OLS equation. And this is the support vector regression. That is another way. So that one does not add up to this. It is a completely new way of getting that. So this is how you estimate the equation that you will have in this context. Now, everything we've done is a simple regression. You can extend the approach to multivariate linear equation. We'll deeply dig into that next week, but there are some important things you want to note. And this is important. One, we can estimate the individual independent variable, their impact on the dependent variable. Matrix is what Excel is using behind the scene, but you don't know. But it's using it. Excel is using matrices. And matrix is kind of indispensable. You can't do away with it. If the number of independent variables are a lot, and you have an intercept, this is it. I've already shown you. So this is an independent variable where you have this time, not even beta, no, you have beta one. By the way, guys, you can use the beta anytime you want. You can even change from beta to alpha, beta, gamma, mu. You can use different Greek letter for different coefficients. Don't worry. So you can have this, and the number of independent variables are now what? Many, up to xk. In that case, this is a multiple regression equation. So I'm just showing you how to formulate. We'll do a proper formulation of a multiple regression equation next time. But watch this. The way this one is written, you can kind of nucleate them, put it all together, combine it all And then you can have it in this format rather. So all I'm doing is that instead of having beta 1, beta 2, beta 3, beta 4, beta all the way up to beta k, you can just say that beta I and then xi, summing all of them plus error. So this becomes all the independent variables and then from the error. This is another way of writing the multiple regression equation. But if you do it in a matrix, and this is important, in a matrix form, I want you to go and prove this. Okay, don't worry, I'll add it to your assignment. Yours is to prove in the matrix form that the beta is equal to x prime x to the power negative 1 x prime y. If you put all of it, you can convert this thing into a matrix easily. Because when you convert it, this one here will become y1, y2, all the way up to yn. Okay, and this alone becomes y. Then the x, okay, the x is several things. So if you have a matrix like this, the x will be something like this, where you have 1, 1, 1, 1, 1 for the beta naught. And then the other one can be x1, 2, x1 that, this one 2, this one that, and then eventually x, kn like that. This is another matrix, which you now call x, simply x. And then the betas, okay, the beta here will be equal to all of the betas, which will carry the same format as the y. So you have beta naught, okay, you have beta 1, beta 2, all the way up to beta n. So all of these betas are now represented by what? Black, bold, beta. All of these x, the independent variables are represented by black, bold, x. All of these y are represented by black, bold, y. And with this principle, you can use the principle of complement and primes, okay, and transpose and all the assumptions of matrices that I taught you the last time. And you can use that to prove that beta cap is equal to this whole equation there. This whole equation is the variance covariance matrix. And you can use this principle to easily find out for the values of every beta. So yours is to go and prove that beta cap is equal to this. And you can start from the original model. The original model will be y equals to x beta plus epsilon. That's it. This is where you start. And once you have that, okay, you can now just by okay. So you can now find a way and then you can prove this. So do that, okay, in your group. Then the next one I want you to do is to prove unbiasedness. Okay, prove that unbiasedness means that the expected value of beta cap equals beta. So I want you to prove that the expected value, this expected value of beta cap is equal to beta. And what do I mean? Well, first of all, we've already said that the beta cap is the estimate, which means that it is not a population. It's from the sample. So it is not a true representation. It's not a true beta. The beta is the population, but you don't know it. It's unknown. And so that's why you collect a sample. And then you use that sample to represent as a representation of the population. But we expect that the value of beta should be equal, the value of beta cap equals beta. And that is called unbiasedness. So beta cap is an unbiased estimate of beta. How do you prove that? Okay, again, using that same equation from above that I showed you earlier, you can use this and prove that this is equal to this. So try that, and let's see. I gave you the half of the formulation here before I gave you the final answer here. So go through and then prove that. It will teach you a beautiful, learning environment. So these are the proof. And then finally, prove that the variance, because anytime you talk about a mean, you also have to talk about the variance. The mean is the expected value. The variance is, yes, Samuel.
Doc, please, with respect to the proof of the expectation, in this case, since the y is dependent on x, the y would be a
Which y
random
is dependent
variable.
on x?
The model.
Yeah.
I don't know whether one will be a random variable and one will not be a random variable, because the x in this case is a constant and the y
Y
becomes
is also a
random.
constant.
Okay, thank you very much.
Yeah. All right. So after you found the mean, or what we call the expected value. So here, this E beta cap is the expected value of beta cap. Okay. So that's the mean. Anytime we find the mean, if you can remember the principle of random variable, and looking at distribution, every distribution, we find the mean, which is expected value, and we also find the variance. So you can prove that the variance of the beta cap is equals to this on the right here. And this on the right is also the same as the variance covariance matrix. So please note, I can rewrite this as base sigma square x prime x to the power -1. Okay. That I can write it like that. That is it in a matrix form. What you see here is not a proper matrix form, but what I've written down there. So what I'm saying, you should prove that the variance of beta cap is equal to what I've written. Prove that, and then you show that. You see all of that in your assignment. So that is simple regression, and then a bit of intro to multiple regression. I'm not going to show you all the mathematics of multiple regression. The only thing I'm going to show you is what I've told you to prove here. Okay. And that will help you. Now, let's go to the real deal for today. And that is the assumptions of regression. What are assumptions? Assumptions are certain things that must be in place before certain things can work. Write it down. You forget it. Assumptions are certain things that got to be in place before certain things can work. So for regression to happen, the following must be in place. One, we must have a random sample of the population. So you must have a population, but you must sample from the population. And the sample is made up of a pairs, XY, XY. So there must be dependent variable and independent variable. Don't just go and collect independent variables and say, I have a sample. You must have it clear in your head, which one is a dependent, which one is independent. And there must be multiple independent variables, as you can see shown here. Now, the next thing is the almighty expected value of the error term. We said that by the time you finish estimating the whole equation, y equals to beta naught plus beta 1 x plus error, by the time you finish estimating it, the error is gone and these ones are capped. That comes from this assumption. The expected value of the error given any of the independent variable is 0. And this, if x is household income and y is consumption, that happens for every household income. The expected value of the error term, okay, given that is 0. And if that is the case, it means that we can now find easily these values. And this value defines a conditional expectation of the y given the s. Please note it. This simply is saying that the mean of the error should be 0. Simple. The mean of the error. And you can go and check our own and then see that principle. In fact, I didn't do it. Oh my goodness. I didn't do it. Let me see if I can quickly do it in the Excel for you. I can take 2 minutes to do that. Well, I think we've not done the regression in the Excel. We'll come to that. Yeah. We'll come to the regression in the Excel. When we do that, I'll show the mean of the error term. So please, let's move on. The next assumption is called heteroscedasticity or homoscedasticity. Homoscedasticity means that there must be no pattern in the variance of the error. Please remember, we are talking about errors here. The variance of the error should be constant. The variance of the error should be constant. The variance of the error should be homoscedastic. Now, opposite of homoscedasticity is heteroscedasticity. What is heteroscedasticity in the first place? Well, it happens when the variance of the error, remember, variance is simply a deviation from the center. When the variance of the error depends on the x. But ideally, it shouldn't depend. It shouldn't depend on the x. So any change that happens in the error is because it's been influenced by the x in the first place. For example, suppose you have household's income. And then we are saying that income affects your consumption. Okay. And then there are households that have low income. And there are households that have high income. Among your data, those with low income might have smaller variance of the error because their spending and their income will be tied closely, very closely together than those with high income. Okay, so what I mean is that when you have plenty money, you don't care about sometimes what you are spending. That's the point I'm saying. But when you have small money, that's when you start calculating. So the variances among those with lower income will be connected, will be smaller than the variances of those with higher income. And that is homoscedasticity. So whenever you have that kind of differentiation of high and low groups of things, heteroscedasticity can happen. And when that happens, you have a problem because there must not be heteroscedasticity, there must be homoscedasticity. That is an assumption that must be there. Understand this assumption because in the multiple regression, we shall correct it all. Next assumption. The next assumption is two errors. The covariance, because there are two, we say covariance. The covariance of the error I and error J should be 0. That word should be 0 means they must not be dependent on each other. The errors are distributed independently. They are actually identically distributed of each other. So what I mean is that if you take, let's say, temperature for person 1, temperature is 78, and then the bottled water sales is, say, 32. Okay. And then for the next person is 80. The bottled water sales is, say, 40, 34. Now, this first temperature will have an error. It will have an error. Let's say the error here is negative 2.4, and the error here is positive 2.9. The two errors must not depend on each other. There must not be any dependency. Of course, this variable, if this one is the independent variable, if the temperature is the independent variable, and you see that very soon, okay, then these two independent variables must also not depend on each other. That is called multicollinearity. And the errors must also not depend on each other. That is called none or zero covariance. So an example, if you have a household and the household have got consumption, and we know consumption depends on income. If that household's particular household consumption is greater than expected, there is no reason to expect that the second household consumption is also supposed to be high. Because they are all in the data set and this one is high, then you're expecting that this one is high relative to the first one, implying a positive correlation. In other words, you are telling me that because they all work in the same company, this one is getting this money, and then this one should be getting this money. But maybe there's other things behind the scenes that's not happening. So this whole assumption is called autocorrelation. There must be no autocorrelation in the regression. There must be no autocorrelation in the regression, in the errors. There must be no serial correlation of the errors. There must be no serial correlation of the errors. I'm repeating that. This is a very powerful assumption in the regression. Another heavy weight of saying that is that the errors must be orthogonal. When people hear these words, they want to die. Don't worry, these are just gargantuan words. The longest word ever used in econometrics is 18-letter words. And that word is heteroskedasticity. And we've already mentioned that and gone. So there's no other difficulty you should ever face. I mentioned that some few minutes ago. Heteroskedasticity. I mentioned it here. Okay, this is it. We've written it. If you check the word, it's 18 letter words. Or it's not. Let me see. 4, 4, 4, 4, 4, 16, 18. If you check. So my point is that you shouldn't be worried about autocorrelation or serial correlation or orthogonality. The errors should be orthogonal. Why? They should not be dependent on each other. Why? They should not be serially correlated. Why? They should not be related. Simple. These are errors we are talking about. We don't want relation. And then normality. Normality simply means combining the two things we've said before. One of them was that the error term must be 0. The expected value of the error term must be 0. And the second one is homoskedasticity. These two, we combine it and we call it normality. In other words, the error here is independently and identically distributed with a 0 mean and a constant variance. That's how you read this. It's normally distributed with a 0 mean and a constant variance. Zero covariance was for the two errors I mentioned here. Look at it. Epsilon I, epsilon j here. That's what I mentioned earlier. But then simply understand that this error, this no serial correlation here or no correlation can be between the errors. If there is no correlation between the errors, if there's correlation between the errors, it's called autocorrelation. If there's correlation between the independent variable, it's called multicollinearity. And we don't want any of these two. If there's correlation between the error and the independent variable, guys, listen. Independent variables are x's. So if there's correlation between two errors, like two independent variables, like xi and xj, this is called multicollinearity. If it is between epsilon I and epsilon j, this is autocorrelation. But if it is between epsilon I and xi, that is called independence. Well, that is called dependency. That is called dependency. And there must be none of these things. So there must be 0 dependency. There must be 0 multicollinearity. Sometimes we make some slight allowance there. And there must be 0 autocorrelation. So these are key assumptions that you want to really understand them as far as the regression is concerned. Then finally, there must be some other petty one, linearity. The relationship between the x and the y must be linear. Okay. I've already spoken about multicollinearity. There must be no perfect multicollinearity. X is deterministic. We've already mentioned that multiple times. There must be no more specification bias. If you can remember, when I was specifying the cells, I was very clear that it was like this, plus the beta 1, temperature, plus the error, blah, blah, blah. Now, sometimes you have to make the temperature square. Sometimes you have to make it a square root and things like that. Whatever you do, there must not be bias in them. So, this assumption, especially the assumption 1 to 4, if they are holding, we say that the OLS estimator is blue. Blue means best linear unbiased estimator. So your beta parameter, the one you are estimating, the organ, Kuchacha, okay, this organ here must be best. It must be best. That's all we are indicating here. And these are what is known as the assumptions of regression. Please keep them. Okay, we'll come back to them later in multiple regression. At this stage, I'm going to end by going to the Excel and showing you how to estimate the regression. This is the data set. I'm going to estimate the regression of temperature on cells. Look at the word I use, on cells. temperature on sales. But actually, it's supposed to be, you estimate the regression of sales on temperature. You estimate the regression of the dependent variable on the independent variable. That is how we talk about it. So how do you do that in Excel? It's very simple. Click on the data tab. Okay, let me just quickly show you before some of you wonder how I did it. It's here, but I'm going to just show it here. So just go to the top here in Excel. We'll do the multiple regression in Python. So click on the data tab on the top right. On the far right, click on data analysis. A pop-up will show very soon. Oh, why is it frozen? No way, no way, no way. All right, we are back. And then in the list, choose regression. Choose regression here. When you choose regression, there you go. Everything is empty. Input Y range. Input Y range is your dependent variable. So you come and click the dependent variable, which in this case is sales, bottled water sales. So click on this, bottled water sales. Oh, come. All right. So let me delete it again. Click on bottled water sales together with the heading and drag it all the way to the end of the data. Input X range, that is a temperature. So click on the temperature, drag it all the way to the end, which is the input X range. Take the labels. This is where I said that, guys, I hope you can see my screen. This is where I said that the intercept can be suppressed. So if you suppress the intercept, it will not even show you the intercept. Okay. And then if you want the confidence interval results, you take here. We don't want it now. If you want the results, output range, click on here and show where you want your results to be. So I want my results to be down here. So I'm just going to click down here. That's where I want the results to be. Now, I want to show you something little about the residuals. So I would also want to take the residuals here. The residuals are the errors. And remember, we said that the mean of the errors is 0. So I want to prove that to you. The expected value of the errors is 0. So click OK, and you will have your regression result right down here. That's it. That's a regression result. Now, everything is plenty decimals. I want the decimals to be 2 decimals. So just go to the Home tab here and click under General, click on the little arrow and select number. Once you select number, everything will be 2 decimals automatically. Your regression is ready. Okay, I'll come and talk about the results. This is simple regression, but I want to quickly talk about the residuals. Watch it. You see, here it has given you the predicted value. See the word it's using, predicted bottled water. We have the actual already in the data, but this is a predicted. And when you take each actual minus a predicted, you get this value, which is a residual. In case you have forgotten, the actual is the one that is above. The predicted is the Y cap, and the actual minus a predicted will give you the residual or the error. So if you like, go and look at the first one. The first one, actual is what? 23. The second is 21, 22. But let's take the actual, 23. So you take the actual, come and look at the predicted. The predicted is 21.8. So the 23 minus 21.8 should give you 1.19. That's the error. That's a residual. Some of them are negative, as we said. Some of them are positive, as we said. Now, the rule is that the expected value, that's it, the expected value of this error should be what? 0. That's what the assumption said. So let's see whether we have met that assumption. We highlight all of this, and then we find the mean. The mean is down here. Look at it. But if you can't see the down here, just go here, type equal to, type average. Okay. And then Select all of these up to the here and enter. Boom. You see that is 0. Your regression has passed. The model is getting better or is better. So this is assumption I wanted to show you. Now let's go to the results here. The most important thing is the interpretation of the result. So how do we get a result? I've already done the results in the slide, so I want to show you. So this is a result of the regression. Of course, you can go through the normal routine of finding the betas that we did. Okay, everything I've shown you here. The beta is 0.67. Okay. You can do that. And then you can now find the result. This is a result I also found. Guys, there are important things you got to know about this result. So in the next few minutes, I'll quickly show you these important things. Number 1, know about the multiple R. The multiple R is another name for the sample correlation coefficient, the one we found. If you can remember carefully, it was 0.93, and this one is truly 0.93. Okay, so that's it. But this is because we are dealing with simple regression. In a multiple regression, it will be different. What does the R square do? Well, the multiple R, okay, square, the multiple R is a correlation coefficient in this case. But when you look at the R square is very important. It's also called the coefficient of determination. It tells you the percentage of variability in the dependent variable that is explained by all the independent variable of the regression. So look at the R square is 87%. The R square is given by RSS over TSS. That is a regression sum of squares over the total sum of squares. And the value is always between 0 and 1. If it is 0.3, it may be acceptable. Anything above 0.3 may be acceptable. The ours is 87%. That's good. Very good. Okay. But what does it mean? What does it mean? In this case, what it means is that 87% of the variation in sales, bottled water sales, have been explained by the entire regression model. That is, it's been explained by temperature, because temperature is the only independent variable. 87% of the variability in sales have been explained by the entire temperature. Then we have the adjusted R square. It's always equal to the R square or less than the R square. The adjusted R square penalizes the inclusion of irrelevant variables. Write it down. Adjusted R square. It penalizes the inclusion of irrelevant variables. So if there are some irrelevant independent variables that you include, and these independent variables are not relevant, but you still include them, the R square will stay the same, but adjusted will come down. Adjusted will come down. And that is what you got to know. The adjusted is given by R square bar 1 minus n minus 1, n minus k, 1 minus R square. It's very, very useful. Okay. But most of the time we use the R square. But when there's a big difference between the adjusted and the R square, you have to check. The next one is a standard error. You can see that down here, 1.18 in this case. It's simply the variability of the observed, the actual from the predicted. Okay, how the actual differs from the predicted in general. If it is small, it means the data is clustered very close to the regression line. Okay. If it is big, it means that the data is scattered. That's it. How do you interpret the coefficient, the most important one? Look down here. The temperature, the yellow highlighted, is 0.673. How do you interpret that? That's the most important thing. Okay. All the independent variables must be interpreted. Okay. It says that first, anytime you're interpreting an independent variable, check whether it's numeric or it's a dummy. A dummy means it's a categorical variable. We'll look at it deeply next time. So once it's numeric, the way you interpret it is different from the way you interpret categorical. In the case of temperature, it's numeric, it's numbers, it's not categorical. So we say that a 1 unit increase in temperature increases sales by 0.673 units. Everything else being equal, ceteris paribus. That's how we interpret it. So it means that temperature has a positive relationship with that. They are all associated positively, by 67, percent. I don't want to use percentage. It's good to maintain the unit without mentioning the unit of measurement. But check whether it's significant. And to check whether it's significant, you have to test. How do you test? Well, the same hypothesis test we did. Okay. So let's check whether temperature is significant. You write a null hypothesis. The null hypothesis is that beta 1, which is temperature, is not significant. That's 0. Or beta 1 is significant. Sorry, the beta 1 is 0, which means it's not significant. Or beta 1 is not 0, which means it is significant. So remember, the first one, when it is 0, is insignificant. When it is not equal to 0, it is significant. This is always a two-tailed test. The alpha is always 5%. And so you use a two-tail. But see, the software has already done all of it for you, but I'm just showing you. So this is a test statistic. Okay. It's just estimated minus the population one, which eventually, this one is always 0. That's what is above here. So it means you are left with this. So you take the estimated, go to the data. Note this. The coefficient divided by the standard error should always give you the t statistic. Write it down. The coefficient divided by the standard error always equals to the t statistic. The coefficient by the standard error equals the t statistic. When you read the t statistic on the table, you will get a p-value. So our value that we are getting is 8.94. If you divide this by that, you get that. When you go and check the results, suppose I hide the one in the table and you do your calculation, you'll get the same 8.97. This is a test statistic. Compare that to the critical value. How do you get a critical value? Well, you find the critical value using this formula, like we always do. N is 14. N minus K. The K is a number of independent variables. And here is only 1. So you go to your table, go and look for the degrees of freedom. The 14 minus 1 is 13. That 13 is the degrees of freedom. It's a two-tail. When you read it on the table, you get 2.16. And this one is less than the 8.9 we found. So it means that the test statistic is truly bigger than the critical value, which means we can reject the null, which said that the variable is not significant, and conclude that the variable is significant. And you can conclude that also easily using the p-value here. All the p-values are 0, which means your error is 0. And as long as p-values are 0, it's less than 5%, which means that the variable is truly significant. So this is the conclusion for that. And you can see I've put the p-value also here. You can use a confidence interval as well. And this is a rule. Anytime the coefficient falls within the confidence interval, it falls within the confidence interval, the lower and the upper, then the variable is significant. Now look at our own. Look at temperature. It's 0.673. Look at the confidence interval. It's between 0.51 and 0.84. The coefficient of temperature, 0.673, falls within. And once it falls within, it is significant. And that is how you conclude with that. So you can use all of this approach to determine whether a particular independent variable, it doesn't matter how many independent. The last but one is the joint significant. That is whether all of the independent variables are jointly significant. Not one, but all of them. In this simple regression, we have only one, but when there are many, you have to use the ANOVA test, the F test. How do you do that? Well, you can formulate the F test and use this F formula. This F formula has some connection with the R squared. You can check that later. When you use this formula, it's already been done. in the Excel for you. But this is how you write a hypothesis, because we are looking at all the independent variables versus the fact that at least one of them is not the same. The null is always that all the independent variables are equal. The alternative is say that no, only one of them is probably equal. All you have to do is to check the p-value for the F statistic. Where is that? Go to the table. Look here. This is a F statistic, the one I've rated them. The F statistic is 79.96. Its p-value is 0. And as long as the p-value is 0, then you are sorted. It's less than 5%, which means that all the independent variables are jointly significant, which means that when you combine all of them together, they can have a bigger influence on the dependent variable. Remember, you can always compare the critical value with a test statistic or compare the p-value with the alpha. Now, our last thing for today is using the regression model for prediction. So this is our sales. Our sales is equal to blah, 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 blah. That's the model. And when we estimated the model, this is our sales. You can see that we have removed the error because in the estimated, there is no error. And the betas are capped because we have the values. Let's substitute the values we had. This is the value. The constant was negative 30.7. And the coefficient, if you can remember, it was 0.673. Now we have this. So let's predict. If we know the value of temperature, can we predict sales? Yes. If we are asked to predict sales without knowing the temperature, then in that case, you use the mean. Take note. If the temperature is 97, what do you think is? Now, when I say use the mean, suppose I want you to tell me the value of sales, but I don't know the temperature. Then all you have to do is I just calculate the mean of the sales, and that's it. And you use the mean to predict, oh, that next year, then sales is going to be this, which is the mean. But what if you know the value of the temperature? What if the temperature is 97? Then you have to put 97 here, multiply the 97 by 0.673, and substitute it, and then subtract the 30.70. And when you do that, you get 34. So it means that if the temperature is very hot, 97, sales will be very high because people are going to buy more bottled water. And what helped us to be able to get this is the coefficient plus the constant. You remember I told you that the constant is not important until during prediction. And I said during prediction and also during something else. So in this case, that is how you do prediction. If the independent variables are many, you have to substitute all of them to get the value of the dependent variable. Ladies and gentlemen, that brings us to the end of the entire caboodle. I know I've gone a little bit fast because of your timing, but take your time, go through this again, and you will see that it is sweet. It is wonderful, and you can still crack this. If you have a challenge at any point, speak about it in the group page. Let me know that I did not understand this and be specific with your question. I will attend to them. The more questions you ask, the more I will have time for you. So please watch this video again and again and understand simple regression. Next time, we're going to take a data set and run these in multiple regression. Now, in that multiple regression, the most important things I want you to note there is that I want you to understand what a dummy variable is and how you interpret it. I also want you to go back and look at how you write your R codes so you're not too surprised. And I also want you to, the assumptions of regression. What if the result is suffering from this? If the result is suffering from this assumption, how will it work? So do that and let me know. If there's any question, please ask. If not, it's been a pleasure talking to all of you. I wish you all the very best. Bye.
Thank you very much.